Hi everyone. In this video we're going to talk about the definition of the derivative and how to find the derivative of a function at a point. So remember that the slope of a tangent line is a limit of the slope of the secant line. We have two ways here of defining the slope of the secant line. The first way here, the average rate of change on the interval a to x is the slope of the corresponding secant line. So we would write out the slope of the secant line as f of x minus f of a divided by x minus a. This is the y value at the right side of the interval at x. This is the y value at the left side of the interval a. And then this would be y2 minus y1 over x2 minus x1. So that's the slope of the secant line. Over here, we use slightly different letters to represent the left and the right endpoints of the interval. The slope of the secant line here, similarly, would be the y value evaluated at the right side of the interval, f of a plus h, minus the y value evaluated at the left side of the interval. And then we would have the x2 minus x1. In this case, the two a's would cancel out, leaving us with just the h. So what we can do now is we can take the limit as the point on the right approaches the point on the left to find the instantaneous rate of change, which is the slope of the tangent line. So what we would do then is we would define the slope of the tangent line as the limit, in this case, as x approaches a, of the slope of the secant line, f of x minus f of a over x minus a. Using this notation over here, it's the same formula, but in this case we would take the limit as h goes to 0. As h goes to 0 then, this right endpoint moves closer and closer to the left endpoint. So then we would have f of a plus h minus f of a all over a plus h minus a, which would just be h. Okay, that's the instantaneous rate of change, and that's the slope of the tangent line for the two cases. And it's just, again, different notation for those 2 points. Okay, well, the slope of the tangent line for the function f is called the derivative of f at a. So this would be the derivative of f at a, and this would be the derivative of f at a as well. So finding the derivative at a specific value, in this case, we'll find the derivative at x equals c, right? And in this case, so here I might use this notation. I'll just shake it up a little bit. We'll say the derivative f prime of f prime at c is the limit as h goes to 0 of f of c plus h. Instead of a, I'll use c here because that's where I want to find the derivative, minus f of c over, I would have c plus h minus c, and then the c's would cancel out, leaving me with just the h there. Using this notation here, I would take this, I would say the limit as x approaches c of f of x minus f of c over x minus c. And both those definitions will give me the derivative at that specific x value, the f prime of c. Okay, so here are some examples. What we want to do in this first set of problems here is we want to look at the patterns here and try to match this up with one of these definitions so that we can find the function f of x and then the value of c, so that we can find where we're trying to find the derivative. In this case, notice we have the h goes to 0, so this follows this pattern up here. And we have 2 plus h, so this would clearly mean that c is equal to 2. 2 plus h, and then we have f of c would be 2. The function, our f of x, would be equal to the 3 times the natural log of x. 3 times the natural log of x. So we would have 3 times the natural log of the 2 plus h minus 3 times the natural log of 2, c plus h and c. all over h. Okay, so what we're trying to find here is f prime at 2, the derivative of the function at x equals 2, or again, that's the slope of the tangent line, the rate of change, the instantaneous rate of change of the function at x equals 2. Over here, we see that this follows more this pattern right here. So we have the x going to 7, x going to c. So in this case, the c would be equal to 7. Now in this case, we can read the f of x right off. It would be this first part right here. So f of x is equal to 1 over the square root of x squared minus 2x. Now we can check that because we should have here f of c. So if we were to plug in 7 for x, we would get 49 minus 2 times 7 is 14. So 49 minus 14 is 35, 1 over the square root of 35. And in fact, that's what we get. And we see we have the x minus 7, the x minus c in the denominator. So this limit here seeks the derivative of f at x equals 7. Okay? It's just a matter of matching up the patterns here. Well, so let's apply this to a problem here and find that actual derivative, f prime at negative 2, if the function is 2x squared plus 1. The first thing we'll want to do here is, well, first of all, let's use this notation here. We'll use the limit as x goes to negative 2 of f of x minus f of c over x minus c, and we'll see how that works. And then we'll try the other pattern. Well, so f of x is given right here. F of c would just be f of negative 2, which would be 2 times negative 2 squared plus 1. That would give us a 4. 4 times 2 is 8. 8 plus 1 is 9. So now I would take the limit as x approaches negative 2 of f of x, which is 2x squared plus 1, minus f of c, which is minus 9, over x minus c, which is x minus a negative 2. This is equal to the limit as x goes to negative 2 of 2x squared plus 1 minus 9 would be 2x squared minus 8 over x plus 2. Okay, well, I cannot do a direct substitution. I can't substitute in the negative 2 here because I get a 0 in the denominator, right? So what I can do is I can factor the numerator by factoring out a 2. So this will give me x squared minus 4 over x plus 2. Well, x squared minus 4 can be further factored into x plus 2 times x minus 2 all over x plus 2. And we see now that we can cancel the x plus 2 in the numerator with the x plus 2 in the denominator, which then allows me to do a direct substitution of the x equals negative 2 into this function, giving me a 2 times negative 2 minus 2. That would give me a negative 4. Negative 4 times 2 is negative 8. So that tells me then that the instantaneous rate of change of this function at x equals negative 2, also known as the derivative of the function at negative 2, is equal to negative 8. For this other problem, it gives me the function f of x is x cubed minus 3 over x, and f prime of x is 3x squared plus 3 over x squared, and it wants me to find the equation of the tangent line at x equals 2. Well, the derivative function here gives me the slope of the tangent line at any point. So recall that the equation of the line in point slope form is going to be y minus y1 equals m times x minus x1, where I have the slope m and I just need a point x1, y1. Well, in this case, x1 will be 2 and y1 will be given by the function evaluated at 2. When I substitute in there 2 into the function, I get 8 minus 3/2, which is, this is 16 over 2 minus 13 over 2 gives me 13 over 2. So my point is at 2 comma 13 over 2. To find my slope, I just need to substitute that x equals 2 into the derivative function. F prime of 2 gives me 3 times 4 is 12 plus 3 over 4. Or if I find a common denominator, this is 48 over 4 plus 3 over 4 is 51 over 4. I can then put that together. I get y minus 13 over 2 equals 51 over 4 times x minus 2. That's the equation of the line in point slope form. If I want to find the equation of the line in slope-intercept form, I just solve this for y and combine like terms. I get 51 over 4x minus, this gives me 51 over 2 minus 51 over 2, and then I add 13 over 2, gives me 38 over 2. I can simplify this down. This is 51 over 4 times x minus 19. So this is the equation of the tangent line. This line will be tangent to this curve at the point x equals 2. And this is the line in slope-intercept form, and this is the line in point slope form. And that's it.